I would like to point out that during this presentation and the slides which are going to be presented, we're going to be able to tackle some kind of issues related to the proper conditions in areas of tunnel ovens and how those conditions are contributing on most efficient, let's say, operation and with minimizing as well the costs. So I would like to start from the beginning, based on which Ms. Kavia has already presented myself. I'm Sevastos. I'm a bakery and food consultant and senior international advisor for European Bank for Reconstruction and Development. And our topic today is effortless techniques that you can implement for your plant, applying some basic rules. A short bio of myself. I'm a bakery consultant. Our mission of Sevastos Bakery and Food is to help business to grow during building, construction, and daily operation, introducing extremely innovative NPD products. Projects which have been completed from my side from Sevastos Bakery and Food is a bakery plant in for El Tajona for food industries in Libya, another plant in Libya, Anrogat Holdings bakery plant as well, a potato processing line for TADCO Agricultural Corporation in Saudi Arabia, and of course, EBRD projects based in Turkmenistan, Croatia, Tunisia, and Tajikistan, based on which we have been applying an implementation of a confectionery plant in Ashgabat. We have been making NPD, new product development for gluten-free cakes and grisinis in Tunisia. We have been observing and optimizing the operations of sunflower seeds processing unit in Khujandi, Tajikistan, apart from making NPD for extruded snacks. And we have been involved in engineering and design from the scratch of a new plant in Split in Croatia, in which we have also included a study and examination and an implementation of shelf-life extension and ambient storage of sensitive food products, for which we have been making a very innovative contribution. My recent projects, the recent projects of Sevastos Bakery and Foods. Bakery plant in Qatar, implementation and final phase of project execution during 2022. New product development for a biscuit plant in Jordan. New product development for a confectionery plant in Greece. Shelf-life extension of water-based fillings. Implementation of a biscuit and chocolate processing plant in Sri Lanka. And of course, collaboration with integrated bakery for a bakery plant in Saudi Arabia. Let's go to the scope, to the main scope of the presentation. The main point for which we are receiving many queries are which are the proper dominant conditions in various areas in a bakery plant. The most important thing and the most efficient step in order to proceed to this kind of determination is to determine the areas in which your process is divided. So dough mixing and forming should be divided and should be separated, having air conditioned, should be air conditioned, having a temperature of 22 to 27, and of course controlled relative humidity, 40 to 60%. If we go to the oven should be separated as well, but in the oven, because of the large heat source, because of the large heat which is radiated from the oven, we should apply air ventilation conditions, for which we are going to refer to the next slides of the presentation. Cooling and packaging also should be air conditioned. Temperature 22 to 27, relative humidity 40 to 60%. So the most important thing, the first step in order to apply air ventilation in areas where tunnel ovens are positioned should be the separation of the areas from the tunnel oven or the ovens, not only tunnel oven or any kind of oven which is in your process. Which are the benefits now? Product quality, energy consumption regarding to the minimization of the energy consumption. Cost reduction benefit in terms of investment budgets, because you don't need to apply air conditioning also in the area of tunnel oven. Employee comfort, which is very, very important, because in the areas of tunnel oven, the temperature and the relative humidity are rather high, optimal performance of machines sensitive to heat, and fulfillment, of course, of regulatory compliance issues, which is very, very important. And we are going to refer to this in the next slides. So regarding the scope, let's take each topic individually. Maintaining a comfortable working environment by applying simple air ventilation. Protection of machines and process from excess of heat and humidity. Dough forming machines, which are operating with dough, seed, or whatever kind of dough, seeded dough or whatever kind of dough. In these areas, by applying air conditioning, you are also avoiding the fluctuation of viscosity of the dough, which is tremendously affected by increased temperature and relative humidity. Financial issues. The large heat loads of non-isolated oven would increase the cost of entire air conditioning of the whole line. So we're dividing the areas, isolating the ovens, and we're optimizing our investment in terms of heating and cooling requirements. Fulfillment of governmental regulations in terms of minimum air ventilation rates. In this table, we are referring to some kind of air ventilation rates which are governed by ASTRA, in which you can see here a room type, which are rather irrelevant to a tunnel oven, but those air ventilation rates and air changes per hour are governing those three, let's say, segments. Offices, based on the number of occupants, 4 to 6. Laboratories, as required for equipment and process, 4 to 15. Industrial kitchens, as required by appliances, we mean here the heat sources, 20 to 30. We can see that this kind of air changes per hour is increasing in some kind of individual areas. General construction guidelines for ovens room by Occupational Safety and Health Administration and by American Society of Heating, Refrigeration and Air Conditioning Engineers. The location of the oven rooms should be in areas with maximum natural ventilation. The construction of the ovens should be in areas with sufficient space at all sides for inspection and maintenance. We must keep the temperatures of combustible floor, ceilings, and walls below 71 degrees Celsius. All unrelated stock or other combustible materials should be maintained at fire-safe distance not less than 750 millimeters from the oven. And of course, the oven location should be in such places that possible fire explosion will not expose groups of operators upon possible injuries. So those are the main guidelines which are manifested and which should be governing the whole design of your plant in terms of safety and of course in terms of efficiency. Air ventilation and conditioning in the oven room. The baking ovens should be residing between mixing, forming, and packaging processes. The air changes per hour based on a general guideline without considering the number of heat sources in the room, meaning that if we're going to have an area with one tunnel oven and we're going to designate this area for 2 tunnel ovens, the air changes rate, the air changes per hour should be governed, should be made in terms of 2 tunnel ovens instead of 1, even though we are going to have 1 oven in the area. Building pressures and makeup air. Sufficient makeup air for an oven room must be provided in order to replace the air moved by the exhaust systems. Negative pressure, which is often the situation which is happening in such areas of tunnel ovens, negative pressure of as little as 0.12 millibar would cause air infiltration through open doors and cracks, causing a backfit in combustion vents, creating health hazards as well as excessive energy usage. This is the most important thing which should be considered in terms of the design of an oven room. Generally, oven rooms having tunnel oven or rotary ovens or whatever kind of heat sources appliances. Options of air ventilation. Let's go to the natural ventilation. This is the first, let's say, topic regarding the air ventilation. This is a system, this is a configuration that often is applied in areas where we have ovens. what is the system is natural ventilation, and which is the principle heat rising on the top, and we are going to have air ventilation from the windows. So we are going to have roof-mounted exhaust vents, and this is a very poor design because air supply is happening from the windows, and from the roof we are extracting the heat without applying the proper air supply inside the oven room. This is the natural ventilation, and this is a very poor design. A second option of ventilation is the negative pressure ventilation, for which we have been referring to the previous slides. Existence of powered exhaust fans on top instead of unpowered. The side effect will be the creation of negative pressure within the oven room, because we are going to have air supply from the windows, and the burners would operate inefficiently owing to the operation of the combustion burners. The negative pressure created is allowing for a combustion system competing for room air which is imposing an inefficient operation. What does this mean? This means that the oven is competing for air because of the burners, and we are also extracting the heat with powered roof-mounted exhaust blowers. This is a negative pressure ventilation. This is often what is happening in areas with tunnel ovens, and this means that we are going to have an inefficient operation. The third option, which is a very good option, is the pressure ventilation system. Makeup air forced in the room at specific spots, lower in the lower edges, up in the top of the ovens, but in the lower, in the bottom, nearby the ovens. Air is forced down to the low levels with heat rising to the ceiling. Unpowered turbines in the roof allow the heated air to leave from the plant. This is a positive pressure ventilation system in which, in comparison to the negative pressure ventilation system, here we are applying air currents with rooftop units in which we are applying air supply covering the air demand of the burners for the ovens to operate efficiently. And of course, we have roof-mounted exhaust vents with which we are extracting the heat. Those positive pressure oven rooms are considered to be better designs. The most efficient now is a balanced pressure ventilation system. The best principle would be the compensation of air consumed in the combustion of the ovens with makeup air distributed in the room, directed downwards to the floor. Exhaust fans powered, located in the roof, would be extracting the hot air which is risen in the ceiling. The main principle would be that the makeup air quantity should be slightly exceeding the exhaust quantity. So we are applying a positive pressure here. We are applying the proper air supply in order for the ovens to operate efficiently. We are going to refer to the calculations how we are going to apply a positive pressure inside the room. And roof-mounted exhaust blowers are extracting the heat. So we are going to have an air movement currents inside by blowing the proper amount of air and by extracting the air and the heat outside. The hot, humid air is extracted, cold air currents are being supplied in the lower point of the ovens. This balanced ventilation air system would be the best design, maintaining oven room conditions having a few degrees of outside. Now, in the next slides, we may proceed having the calculation of the required makeup air in an oven room. For a balanced makeup air with combustion air required for the burners, the total room makeup air must be equal to the room exhaust air. So this is the mass balance equation, which is going to be implemented in order for us to define the QV, the room ventilation airflow. What does this equation mean? Room ventilation airflow plus the burner combustion airflow should be equal with the room exhaust airflow plus the oven stack airflow. This is the mass balance based on which we can calculate and we can define the proper air ventilation, airflow in areas where we are going to have tunnel ovens. In case that burner combustion air is drawn directly from outside, the QB, which is the burner combustion airflow, could be zero. This is rarely happening, of course, in tunnel oven installations, but whenever we have a dedicated airflow being introduced in the zones, in the burners of a tunnel oven, then this could be taken as a zero. Calculation of required makeup air in an oven room. The air ventilation rates, according to ASTRE, would be the required ventilation air supply which would be needed in order to remove the heat loads. In order for us to be able to calculate the air ventilation rates in a tunnel oven, we need to have this equation. This equation is based on the division of the overall all external and internal heat loads by multiplying the air density, the specific heat of air, and the gradient of T, the gradient of temperature difference between indoor and outdoor. So the first step in order for us to calculate the air ventilation rates would be to calculate the overall heat. And which is the overall heat? The total heat is the heat coming from the internal sources, tunnel oven, or whatever else we're going to have as a heat appliance, plus the external heat loads, which are coming from the solar radiation heat, the roof, and the walls transmission heat loads. So the first step is for us to calculate internal and external heat loads. And this equation is going to allow us to define the proper air ventilation in pressurized ventilation systems in the oven. How this calculation is made, in which kind of, let's say, factors this calculation is based. Internal heat loads will be mainly consisting of oven heat loads. The ovens are typically operating between 35 to 45% of their rated burner capacity. 25% of the total rated burner capacity departs the room through the oven exhaust. 25% of the rated heat is needed in order to convert water to steam, in order to make the baking of the product. And the rest heat is remaining to the room, raising the temperature of the product, the oven belt, as well as the internal room environment. So, in general, the estimated oven heat load is 50% of the 35 to 45% of the oven rated capacity. This one is giving us 18 to 22% of the oven's rated capacity. This is how the calculation is made in terms of the internal heat coming from the oven itself. Calculation of required makeup air in an oven room. Another method, of course, instead of using the previous method, another method with which we can estimate the heat gain towards the room would be based on typical heat values coming from the heat rate, the heat rate per mass, which is required for several kinds of products. Let's take an example of crackers. Crackers, they are absorbing, let's say, per kilogram 0.52 to 0.77 kilowatt hour per kilo. So the required heat energy in a cracker production, having 800 kilogram per hour of finished product, the required heat energy would be by the multiplication of 800 kilogram per hour by 0.6 kilowatt hour per kilogram. This is 480 kilowatt hour. This is the required heat energy for baking. The heat sent up to the oven stack is 25% of the 480 kilowatt hour. So it's 120 kilowatt hour. The product heat, in order to convert water to steam, is 25% of 480, which is the overall heat energy. So it's, again, 120 kilowatt hour. The remaining heat transmitted to the room is 240 kilowatt hour. This is the internal, let's say, heat load in areas where we are going to have tunnel ovens. Now, how the other factor in the equation is in order for us to define the overall heat, which is going to be needed for allowing us to calculate the air ventilation rate, is how we're going to calculate the external heat loads. So the external heat loads are coming from the transmitted heat from the roof and the walls. This heat is coming from calculating the area of the roof and the walls, the overall heat transfer coefficient for insulated metal walls with expanded insulation of 100 millimeter thickness is 0.6. This overall heat transfer coefficient is 0.6 watt per square meter per 1 degree Celsius. And of course, the gradient of temperature, which is the difference of the temperature of the walls and roof from the indoor temperature. Combustion air requirements, the QB. In the previous slides, we have seen that the QB, the combustion air requirements in situations where we're going to have burners drawing air from the dedicated air with individual flow of air, I mean. This QB factor could be 0, but in most of the cases, the burners are taking the air from the environment. For natural gas burners, at a stoichiometric combustion process, the minimum air required for complete combustion is 10 times the fuel burned by the oven. So, the nominal value for the energy of the natural gas, because it is 10.86 kilowatt-hour per cubic meter, the ovens are typically, as we have said, burning 50% of their total fuel capacity during a steady state of operation. So the maximum combustion volumetric rate to the burners would be 10 times the 50% of the division of total heat by the heat rate, the energy rate, the nominal value of the energy of the natural gas. We are going to refer with an example upon the calculations needed in order to define the air ventilation. The other factor is to calculate the room exhaust air, QRX, room exhaust air. The exhaust air is drawn out of the room by its ventilating exhaust fans, which are needed to be well distributed throughout the oven room to avoid heat buildup. So this this factor is going to give us the amount of fans which are going to be needed in order to apply a steady operation, a steady airflow, covering the demands of the oven and covering also the necessity of extracting the heat. Room exhaust volumetric rate is the sum of operating capacity of each exhaust fan. This factor is going to give us how many fans, powered fans, exhaust fans, we need to apply in this room where we are going to have tunnel ovens. The other factor of the mass balance equation is the QSX, is the oven stack exhaust. A baking oven exhaust system will typically operate at 25 to 75% of its maximum capacity. So, the estimate of oven exhaust air is the total maximum capacity of the exhaust fans, which is given by the supplier, the manufacturer of the oven, multiplied by 50%. This is half of the maximum capacity of the exhaust fans. If we want now, after all these exhausting calculations and exhausting factors and exhausting variables for the equation, if we would like to join them all together, we are referring to the mass balance. Air ventilation rates, room air ventilation airflow, plus burner combustion airflow. Those two are the air supply towards the oven and towards the room, covering the burning necessities of the oven, should be equal with the room exhaust airflow plus the oven stack airflow. And this is the main mass balance equation which is being applied in areas where we're going to have air ventilation in a tunnel oven. So the QV, the room ventilation airflow, is Q internal plus Q external divided by specific density of the air, and the gradient of temperature difference between indoor and outdoors, plus the 10 times the 50% of the total heat divided by the heat rate of the natural gas. This is equal to the overall capacity of rooftop exhaust fans plus 50% of the total maximum capacity of the exhaust fans of the oven. As we have said, the internal heat is 18 to 22% of the oven rated capacity. So we're having to manufacture an oven, and based on the oven rated capacity, we're calculating as heat which is transferred from the ovens to the environment, 18 to 20% of the oven rated capacity. Regarding the Q external, this is the Q external, which is the other aspect, the other factor in order for us to define the air ventilation, is coming from the multiplication of the area of the roof and the walls, the overall heat transfer coefficient for insulated metal walls with insulation of 100 millimeter thickness. This is 0.6. We're taking some kind of constants here in the equation. And delta T, gradient of T, is a difference between indoor temperature and roof or wall temperature. This is giving us the external heat. Now let's go to the example. Let's assume that we're going to have an oven room, which is constructed by prefabricated steel panels, having 2 tunnel ovens with total heat rate of 1,170 kilowatt each oven, and having, let's say, room dimensions of 73 meters long, 12 meters wide, 6 meters in the height. Assuming that the outside air temperature is 32 degrees Celsius, roof and wall temperature 43 degrees Celsius, and oven's room temperature of 38 degrees Celsius, we have the following calculations. Ventilation air plus combustion air equal to room exhaust plus oven stack exhaust. Ventilation, volumetric ventilation rate is equal to Q total by density, by specific heat of air, by gradient of temperature. So if we need to define the Q internal and Q external, having 2 ovens, the Q internal is 468 kilowatt. All this multiplication is done by assuming 2 ovens, even though we're going to have one, by 1,170 kilowatt, which is the rated heat capacity given by the manufacturer of the oven, by 20%, because this is the average heat which is calculated in tunnel ovens. So we are having the first figure regarding the internal heat. Regarding the external heat now, we are going to have 2 walls, 2 different sides for the walls. We're going to have one roof with 12 millimeter long, 73 meters long, 12 millimeter wide. And this calculation here is giving us 5.69 kilowatt as external heat, transmitted heat from the walls and from the roof. Just to remind you here that we have been assuming roof wall temperature of 43 degrees. That's why the gradient heat, the difference is 43 minus 38, which is the temperature inside the oven. If we could combine those 2 together, 468 kilowatt is the Q internal heat from the oven, as we have calculated here, 468 kilowatt, plus the external heat coming from the roof and walls, divided by the specific density of air, by the specific heat of air, and of course, the difference between oven room temperature and outside temperature. 38 oven room temperature minus 32 degrees, the outside temperature. This is the conversion factor from joule to kilowatt hour, and this equals to 236,800 237,000, let's say, cubic meter per hour. As we have been discussing in the previous slides, the combustion air QB is 10 times the maximum natural gas fuel rate. If we would like also to define the air which should be supplied for covering the burning capacity of the ovens, this is 10 times the stoichiometric proportion of burning of the air. And this calculation here is equal to 1,077 cubic meter per hour. This, the 2,340 is the total rated capacity of the oven, and this is the heat rate of natural gas. And this is giving us this amount. So the total makeup air is the sum of ventilation air QV plus the combustion air QB. And this would be 238, let's say, thousand cubic meter per hour. This is the calculation of a positive pressure air ventilation system which should be applied. And what we can do with this figure? We have calculated in every detail the air which is provided to the combustion chamber of the ovens, and of course the air ventilation rate in order to extract the heat, to create an air movement inside. With this figure, we can calculate the air changes per hour. Air changes per hour is very simple, the division of the volumetric air by the volume of the room. And this division here is giving us, by the overall room volume, is giving us the changes per hour. So this figure is the figure that we have been seeking after all these exhausting calculations. And what we can do with this figure? With this figure, first of all, we can identify if we are going to supply theoretically an oven with air supply in the lower levels of the tunnel oven and rooftop mounting exhaust fans. With this figure, we are firstly examining if we are fulfilling the requirements according to regulatory agencies. And with this figure, we can calculate afterwards by giving these calculations to possibly to manufacturers. We can calculate how many powered roof exhaust fans we're going to install and how many appliances regarding the air supply inside we should define. This is the first figure that is going to be requested by the manufacturer of air ventilation systems, based on which a detailed calculation of a number of exhaust fans which are going to be needed is going to be applied, as well as the air intake appliances which should be provided in an area with a tunnel oven. So this, after all those calculations, we need to define this kind of air exchange rate, which is very important in order for us to be able to design, let's say, our oven room. Now, if we would like to make, apart from air ventilation inside the room, if we would like to make an overview regarding the possibilities of air filtration, this is needed in cases that, apart from air supply, pure air supply, non-filtrated air supply, if we need to define the air filtration in the air intake, then we need to define the minimum efficiency reporting value. This is a classification of the minimum efficiency reporting value dictated by the ASHRAE guidelines. As you can see, we have divisions in the scale from 8 to 11 to 13. According to the classification that we need to define in our room, in terms of minimum efficiency reporting value, we are having here the particle sizes that we can isolate by air filtration. So if we need to make an air filtration as well, we need to classify our room in terms of minimum efficiency reporting value from 8 to 11 to 13. As we're moving from 8 to 11 to 13, we are managing to absorb, to filtrate the air in terms of the minimum possible particle sizes. And this is an exercise that we must make in our room, not only the oven room, in every kind of room where we're going to need air treatment as well. This is an exercise that we need to define in order to define which kind of air filtration we need to have in our room. Do we need to isolate mold spores? Do we need to isolate burning wood, cooking oil, tobacco smoke, smog? Do we need to isolate bacteria? And which kind of particle size of bacteria we need to isolate? From 10 microns to 3 microns to 1 micron down to 0.3 microns. So each room classification is determined according to the particle size which would be needed to be captured. This is an exercise that we must make internally, with which we can define the proper air filtration system. Of course, we are going to have also the possibility of having high efficiency absorbing filters or ultra low particulate air filters. Those filters, by applying those filters, of course, we are having the most proper air treatment according to the classification that we need to define. Let's go to the conclusions of the presentation. Let's go to the summary. To promote balanced heat removal from an area with ovens, first of all, we need to define the proper space around the oven for access and cooling. A ceiling height which would be sufficient enough in order to allow the removal of heat without affecting the ovens which are operating. So we need to define the ceiling height. Distribution of makeup air in low levels and not directly towards the ovens, as we have discussed regarding the positive air ventilation system, the positive pressurized air ventilation system. Withdrawal of exhaust air from the highest points of the room with powered or non-powered extraction fans. And of course, as we have been defining in our equation, the higher the temperature gradient between inside and outside the oven room temperature, the lower would be the ventilation rate, hence the volumetric air supply. This is a general guideline in order for us to define according to our oven room and the height of the oven room and the difference in temperature inside the oven and outside, the outdoor temperature, 10 degrees, 7.5 degrees, 5 degrees. And depending on the room height, 10 meters, 8 meters, 6 meters, those are the air exchange rates, the nominal, let's say, values, dependent upon the temperature difference, which should be applied in an oven room. Those are the nominal rated values which should be applied in an area where we are applying air ventilation and extraction of heat. 10 degrees air ventilation, 10 meters high room, 20 air changes per hour. 7.5 degrees temperature difference between room temperature and outside temperature, 10 meters high, 25. 8 meters high height, 30. 6 meters height, 45. The higher, as we have said, the higher the temperature gradient between inside and outside the oven's room, the lower would be the ventilation rates, hence the volumetric air supply, as indicated in the equation in which we have been referring in the previous slides.